In this video, we will be talking about the addition rules for probability. Our learning objectives are to learn how to decide if two events are mutually exclusive. We will look at how to develop and use the addition rule for mutually exclusive events. And then how to develop and use the addition rule for events that are not mutually exclusive. So let's dive in, and let's begin by defining the term mutually exclusive. Two events are mutually exclusive if they cannot both occur at the same time. That would be events that have no outcomes in common. Let's explore this idea with an example. Example 1, deciding if two events are mutually exclusive. In drawing cards from a standard deck, let's decide if the two events are mutually exclusive or not. If not, list all outcomes that the events have in common. Okay. So let's say we're just drawing a single card from the deck, and we want to know if it's possible to draw a 4 and a 6. Right. So is it possible for both of these events to happen when we're drawing a single card? Is it possible to draw both a 4 and a 6? That's part A. And that's not possible, right? If you draw just a single card from the deck, the card cannot be both a 4 and a 6. A card can't be both a 4 and a 6. Okay. So these events are mutually exclusive. The events are mutually exclusive. Because they cannot both happen. How about drawing a 4 and drawing a heart? You could when you draw one card from the deck, it is possible to draw a card that is both a 4 and a heart, right? The 4 of hearts. Right? You could draw the 4 of hearts. So this is one outcome satisfying both events. One outcome satisfying both events. Okay. So the events are not mutually exclusive. Because they can both happen. Okay. How about part C, drawing a red card, drawing a face card. These are not mutually exclusive either. Because there are several ways you could draw a card that is both a red card and a face card. Okay, so for example, you could get the Jack of Hearts. Right? You get the Jack of Diamonds. Right? Queen of Hearts. Queen of Diamonds. And then King of both, right? King of Hearts, King of Diamonds. So there are 6 outcomes consistent with drawing both a red card and a face card. So those events can both happen, and they are not mutually exclusive. Let's talk about probabilities. The probability of 2 or more events occurring can be calculated by developing addition rules. And this is what we'll do, starting with example 2. Developing a probability rule for mutually exclusive events. So, part A. When drawing a random card from a deck, find the probability of drawing a 4 and the probability of drawing a face card. Okay. Let's start with that part A. Okay. There are 52 cards in the deck, and 4 of them are 4s, right? So the probability of drawing a 4, probability of getting a 4, is 4 out of 52, which reduces down to 1 out of 13. Okay. There are 12 face cards, 4 each of jacks, queens, and kings. So the probability of drawing a face card, so the probability of face card, is 12 out of 52. Let's clean that up a little bit. 52. And that reduces down to 3 out of 13. Okay. Okay, part B. All right, sorry. Part B here. Draw a Venn diagram that lists all outcomes that satisfy these 2 events. Okay. So one event is drawing a 4, the other event is drawing a face card, right? So if I were to draw a Venn diagram, we have 2 events, so my Venn diagram would have 2 circles. We'll label this one for the event of drawing a 4, this one the event of drawing a face card, right? And let's see, I'm going to use this notation. I'm going to use 4D for 4 of diamonds, 4H for 4 of hearts, 4 of spades, and 4 of clubs. Then over here in the face card, and I probably won't have room to list them all, but we've got jack of diamonds, right? Jack of hearts. Just do ... right, to continue. Queen of diamonds, queen of hearts, ... king of diamonds, king of hearts, ... right? But the thing is, there's nothing in the intersection. There's no overlap, right? Because none of the face cards are 4s, right? So there are no cards that are both 4s and face cards. We've got 12 cards that are face cards, 4 cards that are 4s, nothing in the intersection region. Okay. Use your Venn diagram to find the probability of drawing a 4 or a face card. So we can get the total number of cards that are either 4s or face cards by just counting the number of cards in our diagram. There's going to be 12 cards over here, 4 cards over here. That's a total of 16 cards, right? So we can say from part C, probability of 4 or face card is equal to 16 out of 52, which reduces down to 4 out of 13. So then part D, what's the relationship between your answers to parts A and C? Well, the relationship is that if we add the probability of a card being a 4 to the probability of a card being a face card, right, we get the probability of getting a 4 or a face card, right? So we could say probability of 4 or face card is equal to basically just adding the 2 answers from part A, right? 1/13 plus 3/13, which equals 4/13. The answer from part C, right? So that's the relationship. So the method that we used in example 2 provides our first addition rule. When two events are mutually exclusive, the intersection will always be empty. Empty. Okay? And the probability of one or the other occurring is the sum of the individual probabilities. We'll call this addition rule 1. When two events, A and B, are mutually exclusive, the probability that A or B will occur is given by this formula. The probability of A or B is equal to the probability of A plus the probability of B. Just remember that this rule only applies when the events are mutually exclusive. In the Venn diagram, the events are always mutually exclusive if the intersection is empty, right? Because that means that the events can't occur at the same time. The intersection, the overlap there, is only for events that can both occur. Okay, so let's look at another example. A restaurant has 3 pieces of apple pie, 5 pieces of cherry pie, and 4 pieces of pumpkin pie in its dessert case. If a customer selects at random one kind of pie for dessert, find the probability that it will be either cherry or pumpkin. These events are mutually exclusive because if you're selecting a piece of pie, there's no way that it could be both cherry and pumpkin at the same time. It can be one or the other, but not both. Right? So we're talking about the probability of cherry or pumpkin. This is equal to the probability of cherry plus the probability of pumpkin. Up in the problem description, it says that the restaurant has 3 pieces of apple pie, 5 pieces of cherry pie, and 4 pieces of pumpkin pie in its dessert case. That's a total of 12 pieces of pie. Of the 12 pieces of pie, 5 of them are cherry. So the probability of selecting cherry would be 5 out of 12. Of the 12 pieces of pie, 4 of them are pumpkin. So the probability of selecting pumpkin is 4 out of 12. These fractions add up to 9 out of 12, and that reduces down to 3/4. Okay. The addition rule can also apply to more than 2 events. In example 4, we will look at an example that involves 3 events. A card is drawn from a deck. Find the probability that it is either a club, a diamond, or a heart. Right? So in the deck of 52 cards, there are 13 clubs, there are 13 diamonds, and there are 13 hearts. And there are 52 total cards in the deck, right? These are mutually exclusive events because if you pick one card, there's no way it could be both a club and a diamond and a heart, right? It can be only one of those. So we'll say probability of club, diamond, or heart is equal to probability of club plus the probability of diamond plus the probability of heart. Okay. This is equal to 13 out of 52 plus 13 out of 52 plus 13 out of 52, which equals 39 out of 52, which equals 3/4. Okay, what if 2 events are not mutually exclusive? In this case, addition rule number 1 won't work. And it's helpful to think about why. let's say that there is one outcome common to both events. When you add up the total number of outcomes in one event or the other, the outcome common to both will get counted twice, and you'll have one more outcome than you should have. To account for that, you could subtract off that single outcome so that it's only counted once. So this is where our second addition rule comes from. When two events, A and B, are not mutually exclusive, the probability that A or B will occur is given by this addition rule number 2, which says the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. We have to have this subtraction piece because if the events are not mutually exclusive, if we just add the probabilities, the outcomes that are common to both events will get counted twice. We want to count them, but we don't want to count them twice. So this subtraction is a correction, right? So that we subtract off the double counting of the common outcomes. Let's look at an example. A single card is drawn from a standard deck of cards. Find the probability that it is a king or a red card. Okay. So if we were to try to use the addition rule 1, we would take the number of kings, right, which is 4. We'll just say 4 kings. And then we would take the number of red cards, which will be all of the hearts and all of the diamonds, right? And there's 26 red cards. And there are 52 cards total. Right. So if we were using the addition rule 1 approach, we would say 4 kings plus 26 red cards is 30 and divide that by 52. But that doesn't work because 2 of the kings are red cards, 2 of the red cards are kings, right? So if I just take the 4 and the 30, then I'm double counting the king of hearts and the king of diamonds, because those two cards are included in the 4 here. They're also included in the 26 over here, right? So I can't just add them up to get the correct answer because I'd be double counting those. So that's why I have to subtract off the overcompensation. Okay. So this probability would look like this. Probability of king or red card. This is equal to probability of king plus the probability of red card minus the probability of king and red card. Okay. The probability of king is 4 out of 52. The probability of red card is 26 out of 52. Remember, the king of diamonds and the king of hearts is included in this 4. It's also included in this 26. So if I just add these together, I'm double counting those. So to compensate for that, I will subtract off 2 out of 52. Right? That result is 28 out of 52, which reduces down to 7 out of 13. Okay. Let's do another example. 2 dice are rolled. Find the probability of getting doubles or a sum of 6. Okay. So let's consider all the ways to get doubles. So the outcomes would be 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Sum of 6. These are all the ways to get a sum of 6. 1, comma 5, 2, comma 4, 3, comma 3, 4, comma 2, 5, comma 1, right? So there are, what do we have? 1, 2, 3, 4, 5, 6 outcomes that result in doubles. There are 1, 2, 3, 4, 5 outcomes that result in a sum of 6. Probability of doubles is equal to 6 out of 36. Okay. Probability of getting a sum of 6 is equal to 5 out of 36. Okay. There is one way of getting doubles and a sum of 6, right? That would be, you'll notice that, I can just circle it if I want to. The outcome 3, 3 is included in both, right? So we would say the probability of doubles and sum of 6 is equal to 1 out of 36, right? So, using the addition rule number 2, I would say probability of doubles or sum of 6. This is equal to the probability of doubles, which is 6 out of 36, plus the probability of sum of 6, which is 5 out of 36, minus the probability of getting doubles and a sum of 6, which is 1 out of 36. That ends up equaling 10 out of 36, which reduces down to 5 out of 18. Okay? Let's look at another example. In a hospital, there are 8 nurses and 5 physicians. 7 nurses and 3 physicians are females. If a staff person is selected, find the probability that the subject is a nurse or a male. So for this one, it would be helpful to make a little table. So we'll make a little column here, which we'll label nurses, physicians, and total. And then we've got females and males. Okay, so I got this little table here. So there were 7 female nurses and 1 male nurse. Right? We'll also do a total over here, for a total of 8 nurses. There were 3 female physicians and 2 male physicians, for a total of 5 physicians. Do our totals like this, okay? If I add up the columns, 7 plus 3, there were 10 females, 2 plus 1, 3 males, for a total of 8 plus 5, 13, okay? 13 individuals. So, if a staff person is selected, find the probability that the subject is a nurse or a male. Okay, probability of nurse or male. This is equal to probability of nurse plus the probability of male minus the probability of both, right? Nurse and male. Probability of nurse. Well, there were 13 people, and 8 of them were nurses, right? So that would be 8 out of 13. Probability of male. 13 people, 3 males. 3 out of 13. Nurse and male. There were 13 people. One of them was both a nurse and a male. So that would be 1 out of 13. This is equal to 10 out of 13 when you work that out. Okay, so that's it for this video. So those are some really helpful formulas for finding the probability of one event happening or the other. One version of the formula works for mutually exclusive events, and the other one works for any events, including events that are not mutually exclusive. So we'll wrap this up here. Thank you for watching.